The question here is asking about how many trainable weights and bias terms are there in a convolutional network, for example, like this. So let's start from the first convolutional layer. So first, we know it's a 5 by 5 filter. Given an input image of 22 by 22, we are getting, so for example, if we want to get this activation matrix, so let's call it A1, 1. To get this, what we are doing is we just put the filter on top of this pixel, and we'll get the corresponding pixel, and then we move this filter around and get the next one, and so on. So the thing here is that there is only one filter, and it's the same filter applied to all of them, all pixels. So we only need to train for each one of the activation maps or activation matrix, we only train a 25 to 5 by 5 filter, which there are 25 weights in the 5 by 5 filter. So for each one, and there are 6 of them. So this is A2, this is A3 until A6. There are 6 of them. So we have 25 times 6 weights in this layer. So one thing that's done slightly different from what I had in the lecture is that the original input is 32 by 32, and the resulting one is 28 by 28. So what basically happened is the convolution I did in the lecture has zero padding. So I assume all of the stuff outside this image is zero. Here we are not assuming it. So the first element here, the first convolution here correspond to this 5 by 5 block. And there are basically 2 rows and 2 columns that will not have a corresponding convolution activation in this activation matrix. So we have 2 less columns on the left and 2 less columns on the right. So there are in total 4 less columns and rows similarly. So that's why it starts from 32 to 28. So that's a small problem. And also in the original paper, there can be bias here. So if you have a convolution and you can just add a bias for for each activation, but we're not going to do it here. But if there are bias terms for convolutional layers, then there should be 6. But again, we're not doing it here. So on the exam, I'll make it very clear that we won't have bias terms for convolutional layers. And the second layer is the subsampling layer, which we are calling the pooling layer. So there are 2 types, the max pooling and the average pooling. So the max pooling is just you take a 2 by 2 block, and then you find the maximum of these 4, and then you just put it here. So the reason why I know it's 2 by 2 is starts at 28 by 28, and then at the end it's 14 by 14. So basically each 4 gets turned into 1. Each 4 pixel get it turned into 1 pixel, so that's why I know it's 2 by 2. So here, if it's the max pooling, there's nothing to train, and if it's the average pooling, there's also nothing to train because it's just 1/4 of this, plus 1/4 of this, plus 1/4 of this, plus 1/4 of this. You get that number. So in any case, there are 0 weights to train. And again, in the original paper, it's done slightly differently. What was done is you have that number that I talked about. Basically, for example, if it's max pooling, then I have the max of the 4. And then what the authors did is they multiplied by a W weight plus and added a bias B for each of them. So it turns out there are 2 times 6, so 12 weights. But again, we're not considering this for this course, so we don't have these weights basically. And again, I will specify on the exams very clearly that also the pooling layers will not have weights and bias terms. Okay, so the next one is we started with 6 activation matrices and now we have 16. So if we have fully connected convolution layers, then there should be, and also know that it's 14 by 14 to 10 by 10 again, so it's subtracting 2 on both sides. So these are 5 by 5 filters again. So there are 25 in each filter, and there is one filter correspond to from this one of these 6 maps to one of these 16 maps. And similarly, there is one filter connecting this activation map to the same one and similar for the other one. So there are in total 25 times 6 times 16 number of weights. So again, the problem is in the original paper, it's not fully connected. So I remember it's like the first 3 is connected to the first one, and the first 4 is connected to the next one, and so on. So basically, it's not all 6 are connected with all 16. So you have basically less. It's possible to create a network that's not fully connected. So it's only a subset of these are connected to a subset of these, for example. So there could be less. And similarly, for the next subsampling or the pooling layer, we convert 4 to 1 because it's 10 by 10 to 5 by 5. So there are 0 weights. And the next layer is a fully connected layer. So basically, the way to think about this is you can just flatten all of these 16 matrices and make a very long vector, and that vector will be 16 times 5 times 5. This is the vector length, and then that vector is connected. The first one is connected to first, second, and third, and so on. The second one is also connected to first, second, and third, and so on. So it's fully connected. So there are this many units in the previous layer, this many units in the next layer. So it's just like a regular neural network. There are this many weights. So an alternative way to think about this is you can have a 5 by 5 filter on top of this, which the image is 5 by 5. So when you filter it without zero padding, again, we have subtract 2, subtract 2. Basically, there's only one unit left. So you can think about this full connection layer as a convolutional layer, as suggested in the original paper as well. But the way I think about it is just flatten this into one large vector, and then it's just a regular neural network with 4 connections. So, and then the next one is the same. So there are 120 units in the previous layer, 84 units in the next layer. So there are this multiplied by this weights. And the last one is the same. So 84 times 10 weights. So the total number of weights, excluding the bias terms and excluding some of the weights for these pooling layers that is in the original paper, but we are not considering them. You just add all of these numbers up, you get total number of weights.